The principles behind which NMR works are pretty straightforward and easy to follow, but it can, at the surface, appear very complicated. And so what I'd like to do in this video is go over how we go from the raw data that comes out of an NMR machine and produce the spectra that the chemists will use to actually analyze the molecule. And so let's take, for instance, a water molecule. We know we've got two protons, and these protons will spin either with or against the applied magnetic field, commonly denoted B0. And as we're applying this magnetic field, these spins will rotate with some kind of precession. And this precession, referred to as the Larmor frequency, is something that is detected by the radio frequency transmitter. And the radio frequency transmitter will output some voltage at a given time. And so what we end up with is raw data just in the form of a voltage and a point in time, like this graph here. And so this graph exists in the time domain. And if you just plotted the raw data coming out of your RF transmitter, this is what you would find, for instance, with water. And so we see that we've got this decaying sine wave. And what we'll note is we can visually see what the time between peaks is, the period, as well as this kind of decay rate. And what this will do is it'll allow us to very easily visualize what kind of spectra we would expect to find. And so a term that you'll hear NMR people toss around is Fourier transform. And it sounds a lot more complicated than it is. There are math equations behind it, but we always use computer programs to evaluate that kind of stuff. But what happens when we Fourier transform a function in the time domain is we end up with something in the frequency domain. And in this frequency domain, because we were able to determine, in this example, we've got a period of 0.125 seconds. Therefore, it has a frequency of 1 over t, which is equal to 8 hertz. What that means is in the frequency domain, after we've taken the Laplace transform, at 8 hertz, we're going to expect to find a signal. Now, what will make this peak different is this peak will have a certain width to it. Because our signal is decaying, it will have a peak width that's not equal to 0. And so the faster this sine function in our time domain is decaying, the broader our peak. And one of the ways we can determine what noise is in our NMR spectra is the noise, such as a 60 hertz wall outlet, which will appear in our raw data commonly, is stuff that is constant for all time. And because it's a constant, its decay time is technically infinity, and it appears as kind of a Dirac delta function in our Fourier transforms. And so with these decay signals, what we find is if we analyze the time it takes from the initial peak, which has an intensity of 1, to get to about half that intensity, that occurs after approximately 0.5 seconds. And so what we're going to do is we turn to an equation, and this is delta nu 1/2 is equal to 1 over pi times t 1/2, where t 1/2 is this decay time that we just analyzed. So we're going to plug this into this equation, and if we evaluate it, we find that we'd have a peak width of approximately 0.5 hertz, or 0.6, but you get the idea. And so what this tells us is that when we take the Fourier transform of our time domain data, we're going to get some kind of peak that looks like this. And usually these peaks are a little bit sharper, but we get the idea. The width of this peak will be about 0.5 hertz, and it will appear at 8 hertz. And so we can visualize very quickly what the NMR spectra should be just off the time domain data that we have coming out of the RF transmitter. And so I thought this would be a nice introduction as to the way we're able to process NMR data and actually use it in practice, so we can see chemical properties and analyze new molecules and deduce the structures of unknown compounds. And so it is pretty interesting stuff. I hope you guys find it useful. Let me know if you have any questions, and thanks for watching.